Okay, 3.4. So I don't really like this section because it's sort of just a review section. Generalized statistical interpretation is basically a fancy way of saying, okay, we're going to formalize sort of the theory behind everything you've done in this textbook up until now. And Griffiths sort of does it in a very weirdly roundabout way, and I feel like it's a bit unnecessary, so I'm going to skip some parts of this section and sort of just emphasize the most important thing, because what he does is he emphasizes the interpretation itself, and then he does like 2 examples. I'm not really a fan of the first one because I feel like it's redundant, so I'm going to skip that one and go straight to the second one, because that one leads into something more important, which is the distinction between momentum and position space. But we're getting ahead of ourselves, so let's just summarize this real quick. So the generalized statistical interpretation is effectively just a fancy way of summarizing everything we've learned up until now. And essentially in quantum mechanics, right, so far what this textbook has taught you is that you are generally working with 2 types of problems. The first type, whoops, what is happening with my pen? There we go. The first type is effectively you're trying to find the wave function itself. So, whoa. Okay, give me 1 second. My pen is acting up. Okay, there we go. That's better. Sorry about that. Okay, so everything you've learned in quantum mechanics up until now can fundamentally be boiled down into 2 types of problems. The first one is basically finding the wave function psi. The second type is if you're given psi, then you're trying to find the probability that, you know, some operator that represents an observable, q hat, is in the range of EQ. So, for an example, in problem 2, or in the second case, this would be like, you know, what's the probability of finding the position of the particle between this range and this range in something like an infinite square well or a simple harmonic oscillator. In other cases, you might be trying to just find something that's determinate instead of in a specific range. For example, energy, right? What's the energy of the ground state of the simple harmonic oscillator, and so on, and so on, and so on. So the generalized statistical interpretation is basically going to say, okay, we're going to basically sort of tell you just sort of formally how to do the second problem, and from there you can sort of reverse engineer the process in order to do anything you need to find the first problem. And it's not really a method, it's more so just formally sort of putting everything that we know into a single statement. So let's just write it out. What it's telling you is, okay, so given psi, if you have some observable that represents, you know, that's represented by an operator, Q, in terms of X and P, what this is saying is that, okay, if you measure Q hat on psi, assuming that it is an observable, you will get one of the eigenvalues of the Hermitian operator. So what it's saying that, what it's effectively saying is if we operate Q hat onto psi, we will get an eigenvalue of Q multiplied by psi in the eigenvalue equation. And this is kind of obvious because we literally just spent the past 3 sections going over this. But this leads to 2 situations. So situation 1 is that Q is discrete. So Q is discrete. What this means is that you're going to get specific eigenvalues, right? Like the eigenvalues are specific. It's this value, it's this value, it's this value, it's this value. So let's label those eigenvalues Qn. I'm going to say each Qn has, you know, some associated eigenfunction, Fn, and the probability of sort of finding this specific eigenvalue when you measure Qn is equivalent to the coefficient, Cn squared. And you find the coefficient through Fourier's trick, which we did multiple times starting from chapter 1. So Cn is going to equal the inner product between your corresponding eigenfunction and the actual wave function of interest. So we already know this, right? That this I don't think I have to elaborate on this more, because this is just retreading what we talked about starting from chapter 2. In case 2, Q is continuous. So an example of something of sort of an eigenvalue that's discrete would be energy, right? Because energy takes on distinct values that are indexed by n. In contrast, if Q is continuous, then you're working with something like position or momentum, where sort of the corresponding eigenvalues take on a function, right? So now you have Q in terms of some index z. And the corresponding eigenfunctions are going to be f of z, so each z is going to have a corresponding eigenfunction, f of z of x. And then, now your probability is going to be equal to magnitude c of z, because now your coefficient, because of the fact that there's a coefficient for every single eigenvalue, and the eigenvalues are continuous, the coefficients also form a continuous function of z, into magnitude squared of that, and you have to integrate it over dz. And then similarly, the coefficients c of z is just going to be equal to the inner product of the eigenfunction of f sub z with psi. So this is, once again, something that we learned back in chapter 2. It's the exact same thing. Or I guess in this case, this would be chapter 3. And then the third point, which is something we established back in chapter 1, is that on observation, the wave function psi collapses. So remember how, back in chapter 1 we said, okay, we observe a wave function and we find that it has some observable value at some specific value. The wave function collapses around that value. And now, for that moment and for the foreseeable future, you have a 100% chance of seeing that wave function be like effectively a Dirac delta 100% given on whatever value observed. So that's also something that we already know. It was covered back in chapter 1. So, this is kind of it. This is what the generalized statistical interpretation is. So just sort of as an example, let's try to apply this to momentum. So we already know, well, okay, let me write this out. Example, momentum. So we already know that the eigenfunctions of momentum take on the form of fp of x is equal to 1 divided by square root 2 pi h bar multiplied by e to the power of ipx divided by h bar. So if you want to find the corresponding coefficients, c, right, then cp, so remember momentum is a continuous eigenvalue, right? So let's write it like this. So c of p, right, is going to equal the inner product of the momentum eigenfunctions with the wave function itself. So this is therefore going to equal 1 over root 2 pi h bar. I bring that out of the integral from negative infinity to infinity. Remember, this side has to get conjugated, so now it's e to the negative I px over h bar. And then we're multiplying by psi of x comma t. And that's it. That's all that this example does, is it's showing you how we would apply sort of a situation like this. But specifically, the reason why this one is important is because this specific integral, this is a very important integral. And the reason why it's important is specifically because of the fact that we already know that any observable can sort of be decomposed into a combination of position and momentum wave functions. So before anything, let's define something. We're going to call this momentum space wave function. We're going to call it phi sub p of p comma t. This is basically saying, okay, well, this is sort of fundamentally the exact same thing as a standard wave function, but instead of sort of looking at the wave function over position, you're looking at it over momentum. And what you will realize is that this is just effectively a Fourier transform of the position space wave function, psi of x comma t. So if we went over Plancherel's theorem a little while back. I don't remember which problem it was, but it was basically saying, okay, hey, you can take a Fourier transform of psi of x comma t and turn it into something in terms of momentum instead of position. And you can do the same thing with the position wave function and transform it back into a wave function of position instead of momentum. So just sort of to cover all our bases, the definition of Plancherel's theorem is basically saying, okay, we can take a Fourier transform of our wave function and get basically, okay, phi of p comma t, our position space wave function, or sorry, our momentum space wave function is equal to the Fourier transform 1 over root 2 pi h bar, integral from negative infinity to infinity, of e to the negative I px divided by h bar, times our position space wave function, psi of x comma t, dx. Similarly, if we want to transform back, well, the position space wave function x comma t is just going to equal a Fourier transform 1 over root 2 pi h bar, integral from negative infinity to infinity, of e to the positive ipx divided by h bar times phi of p comma t. So fundamentally, phi and psi sort of represent the exact same thing. They're both wave functions that define a system. The reason why they're different is, well, sort of the only thing that they are different in is phi deals with momentum and psi deals with position. And what this does is it's significantly easier to find some, like if you want to find the probability of the momentum of some system being in some range dp, it is significantly easier to use this, because in this momentum space wave function, it turns out that p hat is just equal to p, and it turns out that x hat is going to be equal to, I h bar d by dp or something like that. I didn't memorize the exact formula for this, but it's something like that. Basically, the roles of the x and p operators reverse. So if you're dealing with, something like some sort of observable that is heavily dependent on p, it might be easier to just use sort of this momentum space wave function instead of the position space. Because, if you have a q hat that's equal to, like, I don't know, p hat squared minus p hat divided by p hat plus x hat or something like that, it might be easier to work with something like this in terms of momentum space, because the p hats just become p's, whereas the x hat is the thing that transforms into that complicated I h bar d by dp. So because of that, sort of depending on what sort of system you're looking at, and also depending on what sort of observable you're trying to find, you may want to use one or the other, because choosing the correct one typically makes your math significantly easier. So with that, let's move on to an actual example. And after that, we will finish up and start working on the problems. Okay, so 3.4 is going to show us sort of this simplification of using momentum space in action. So suppose that you have a delta function well. So you have v of x is going to equal negative alpha, which is some factor, multiplied by a Dirac delta of x. We want to find the probability that momentum is greater than p naught equals m alpha divided by h bar. So instantly we're working with momentum. This implies that maybe we want to switch to momentum space instead of position space, right? So let's do that, right? The bound state potential wave function, specifically from chapter 2.5, is defined as psi of x comma t is equal to the square root of m times alpha divided by h bar times e to the power of negative m alpha times magnitude of x divided by h bar squared multiplied by e to the power of negative I et divided by h bar, where E is the energy and E specifically equals negative m alpha squared over 2 h bar squared. So, whoops, let's just fix that. There we go. So in a bound state, in a delta well, there is only one valid bound state with one valid corresponding energy. So we're working with momentum. We want to convert to momentum space to make our math easier. So let's do that via Plancherel's theorem. Phi of p comma t is going to equal 1 divided by the square root of 2 pi h bar multiplied by square root of m alpha divided by h bar. And then we're going to pull out the e to the negative I et divided by h bar. So e to the negative I et divided by h bar. And we're integrating from negative infinity to infinity of e to the negative I px divided by h bar times e to the negative m alpha times magnitude x divided by h bar squared, close off of the dx. So if we can solve this integral, we can get a momentum space wave function, and from there finding the sort of the probability of p being in some range is very simple, because it's literally, you know, just integrating this momentum space wave function from one value to the other. So that being said, this is kind of a pain in the ass to integrate. So Griffiths just sort of throws it into a calculator. I'm going to do the same. So this whole thing is going to eventually end up equaling square root of 2 over pi multiplied by p naught to the power of 3 halves times e to the negative I et divided by h bar divided by p squared plus p naught squared. So then if this is equal to phi p comma t, right, we're trying to find the probability that our momentum is in some given range, specifically greater than p naught. So according to, you know, the generalized statistical interpretation, what we're trying to find is basically probability is equal to the magnitude of phi squared times our range dp. And we're going to integrate this. And this is a little bit confusing because probability also begins with p. This is probability. So if we integrate over our given range, this is going to give us, well, we're going to take everything squared, or magnitude squared, so 2 over pi instead of root 2 pi. And then we're going to get, let's see, we can pull out a p naught squared. Well, let's just keep it as is. So this term is going to cancel out because it's a complex number, so multiplied by its complex conjugate is going to give us 1. Multiplied by the integral from p naught to infinity, because remember, we're trying to find the probability that our momentum is greater than p naught, and then this whole thing. So p naught to the power of 3 halves divided by p squared plus p naught squared dp. And, you know, p naught is just a constant. So realistically, what this is really asking is just integral from p naught to infinity of, you know, some constant divided by p squared plus some other constant dp. And you can throw this into a calculator again. It's going to give you like 0.09 or something like that. So what we've done here is basically just made it significantly easier to find probability, but we had to do sort of a trade-off in that we have to do this significantly harder integral to actually convert our position space wave function into a momentum space wave function. So, you know, now when we work on problems, it is going to start turning into sort of a balancing act where it's like, okay, is it worth it to turn it into a momentum space wave function, or should we just stick with a position space wave function and just deal with the added difficulty of working with a p operator? Or is it worth it to do this complicated integral and go into momentum space and then do a very easy integral afterwards to find the probability, and so on and so on. Sort of once you get into higher levels, just in general, you'll have to start looking at these kinds of trade-offs more and more, because the integrals just get more and more complicated. Of course, there's also the option of just sort of blindly throwing everything into a calculator but you're going to run into a lot of integrals that technically are either unsolvable or will take a computer an extremely long amount of time to solve, and sort of at that point your work becomes sort of trying to simplify the problem so that the computer can finish the problem in a span that's less than 1,000 years, stuff like that. But as of right now, sort of we can just confidently say, okay, whenever we see something that wants us to solve something in terms of p, or like is something that's very heavily involved in terms of momentum, it's just, let's just by default try to convert it into a momentum space wave function and just assume that it'll be easier to work with it from there. You can worry about things like whether or not it's worth it to do the conversion when you start working with significantly more complicated problems if you ever take a graduate course in quantum mechanics. But for this point and for now, it's effectively safe to just assume that, okay, if you see a lot of p's, convert into a momentum space wave function. If you see a lot of x's, stay in position space. And with that, we are done with 3.5. Or sorry, 3.4.